Yeah. Yeah. Hello. Yeah. Yeah. Hello.
Hello, Acharya. How are you? Oh, my goodness.
Hello.
Hi, Acharya. How are you?
Yeah, I am fine. Yeah, I could not come to your TBS talk.
Oh, that's okay. Don't worry. Yeah.
Yeah. So, how are you doing?
Oh, fine. Thank you. Yes. Hi, Sukant. I think so. It's okay.
Hello.
Hi, how are you, Sukant?
I'm good. How are you?
That's Zinda, huh?
अरे
I
काफी
think-
कमाल कर रहे हैं.
I think you'll have to poke me and see.
Start, sir. Good afternoon, everyone, and welcome to another session of Asset Colloquium here. We are very lucky to have a very prominent professors and one who has been closely associated with giving asset colloquiums to TFR. As he told me today at the lunch table that he's just near the peak of being the highest number of asset colloquium given from TFR here, and he's hoping to summit that. So I welcome Professor Deepak Mathur here to give an asset colloquium on behalf of assets. This audience doesn't require much of an introduction about him, so I'll go through the process.
Thank you, Parag. And thank you also to Satya for helping arrange this. As he's indicated, for many years, Satya used to maintain a list of the number of people and how many colloquia they've given. And I used to be top of that list for many, many years. But after I retired, some young upstarts like Mayank Varia and Arnab Bhattacharya, they started giving talks and more talks and more talks. So now the net result is both Arnab and Mayank are one more than me. So at 5 o'clock today, I'm hoping that I would have caught up with. And then I'll have to try and find some work to do or something to report so I can then overtake them and hope that those two don't. Okay, so let me just start by telling you a little bit about the title. What does all this mean? So using nanoparticles as catalysts seems pretty self-explanatory. I'll come to that later. For exotic molecular processes. So what do I mean by exotic molecular processes? The one specific process that I'll be talking about concerns water molecules, H2O. I'll show you what a water molecule looks like according to 6th standard chemistry textbooks. Good enough. And you will see that the sort of reaction that I want to talk about is rather exotic and it's unexpected and shouldn't normally happen. In intense laser fields, well, you've heard lots and lots of talks in this hall of what is meant by intense laser fields. Just to recapitulate, if you take a hydrogen atom, you have an electron, which is supposedly going round and round, the nucleus, the proton, and what is holding the electron to the proton is the Coulomb field. Now, if the external field experienced by the hydrogen atom is as it is normally, it's very much smaller than the Coulomb field, and therefore the hydrogen atom is a stable entity. We know that, it's not a surprise. The electron stays bound to the hydrogen atom. However, if you have a technique whereby you can have an external field which can be increased as you crank the external field up so that it gets higher and higher and starts approaching the Coulomb field that is binding the hydrogen atom together, then you have reached a situation where the electron no longer knows whether it belongs to the Coulomb field over here or it belongs to the external field, from whatever means you've generated that external field, and therefore spontaneous ionization takes place. And that is what I mean by atoms in intense laser fields. Now getting back to the first part of the talk, which is using nanoparticles as catalysts. So before I explain to you what exotic molecular process I'm going to focus on, I should mention what I mean by nanoparticles as catalysts. And there are two slides in my talk today, which my grandkids encouraged me to use artificial intelligence to generate. I actually tried to use AI, ChatGPT, to generate the entire talk. And it did generate a talk, but it was junk. It was total rubbish. So you have to be very careful. But I'm quite pleased with the two AI-generated images. And this is one of them. And you'll see my images are never as, those images generated by me are nowhere near as colorful as this. So it shows a satellite in fairly low Earth orbit, and it's actually losing the orbital status. It's unstable. It's starting to enter the Earth's outer atmosphere. And as it enters the outer atmosphere, it starts encountering friction. And as it encounters friction, it starts getting hot. And this is what you see, a plasma being formed because of the frictional forces generated on the satellite surface. It just so happens that it's happened above India. I asked ChatGPT, do it over India, and ChatGPT could do that. Wonder if it's illegal to show this photo, because I noticed going into the colony, it says no drones allowed. Well, this is a fancy drone. I mean, it's a bit higher than normal drones. So please do not tell the powers that be in the Institute or in the Navy that this photo is being shown surreptitiously. Huh? Oops. You see? This is what old-timers like me are not used to. So it's not my slide, it's ChatGPT. So, okay. So what causes the satellites to ultimately break apart and ultimately burn up in the Earth's atmosphere? Well, I've already said it's because of atmospheric drag. The reduction in the altitude of the Earth's orbit results in greater and greater atmospheric drag. And at lower altitudes, there is a denser atmosphere. Therefore, there's increased drag. Therefore, there's increased heat. And usually, there's a lot of burning on re-entry. Sorry. Now, meteorites also burn up as they enter the Earth's atmosphere. So how do I know that this sort of picture that I'm showing you is of satellites which are burning and not a meteorite? Well, meteorites are mostly rock. So it's, if you look at it with a spectroscope, oxygen, magnesium, silicon ions are what you would expect to see if you pointed your spectroscope at these things. Satellites, of course, are mostly aluminium. And there is some aluminium in meteoroids, but it's usually less than 1% of the total abundance. So if you happened to be lucky enough to see one of these in the night sky, and you also happen to have a spectroscope in your pocket, you'd be able to tell whether you're looking at a meteorite or a satellite burning. How many of you carry spectroscopes in your pocket in the night? Not many, right? So there will be another way of distinguishing, okay? Now, this is the second ChatGPT slide. The satellite is now much lower. It's not visibly over India now. So I'm safe, Vandana. You don't have to send an SMS to the naval commander. And you can see that the plasma seems to be much hotter. There seems to be ablation going on, lots of particles being emitted and so on and so forth. And it's very close. Sorry? Oh my goodness. Is it Jammu and Kashmir? No. What's that water then? Please don't get me into further trouble. I'm told one has to be very careful in Tata Institute these days. Oh, you're the dean as well, so I have to be even more careful. You're here. Oh, you're not there. Oh, no. Okay. Okay. Now, these are examples of Starlink satellites falling out of the sky. Starlink is a satellite system put up by Elon Musk Elon Musk is now going to be an important functionary in the government in Trumpistan, in the US, sorry. And that'll again get me into trouble now. So one has to be careful. This was fairly recently, September 2023, in the sky over Puerto Rico and the Dominican Republic. Again, how do I know it's not meteorites? Well, how do you tell space debris from a meteorite or from a meteor that is falling out of the sky? There are two main characteristics. One is the space debris appears as an extremely slow meteor. So it takes about 1 minute to 2 minutes to cross the sky as you're watching and looking in your pockets for a spectroscope. Okay, whereas a meteor will take just a few seconds at the most to zip across the sky. Zip across the sky. Okay, so that's one very easy non-spectroscopic way of knowing what is what. And the other indication is that there is a very noticeable fragmentation in the case of space debris. Okay, so you can often see small objects separating from the main. Well, it's not very clear over here. Initially, when it started, there was only 1 or 2 flashes of light, and as the satellite has disintegrated, you see many more flashes of light as the satellite has broken up. Okay, so what's the big deal, right? So where do nanoparticles come into it yet? We haven't reached that yet. Okay? So what has space debris got to do with this talk? Okay, now the point that I wish to make is that nanoparticles are formed in the course of satellite re-entry into the Earth's atmosphere. That's because there's intense heat that is generated. 1500 Celsius is typically the estimate that is there, and a very large amount of pressure that is experienced during descent, and the descent is at very high speed, so there's a lot of friction. And all these contribute. The heat can cause the satellite materials to vaporize and to form a plasma. The satellite materials, as I've already indicated, are mostly metallic, or it could be ceramics and composites as well. Now, the formation of nanoparticles can occur because of ablation and vaporization, which is what ChatGPT was trying to show. And it's probably right. That's probably how it occurs. Satellite material heats up, undergoes ablation, and the vaporized particles can condense into smaller particles, including nanoparticles. There can also be plasma interaction. The satellite surface interacts with the plasma. Rapid cooling and presence of ionized particles in the plasma can lead to the formation of nanoparticles, much as you would find form nanoparticles in a lab on this floor in Tata Institute. Okay. Now, these nanoparticles in the Earth's atmosphere have an environmental impact, and I want to stress on this, that the environmental impact may be very important and very significant. First point is that there's an atmospheric distribution. The nanoparticles can remain suspended in the upper atmosphere for long periods of time. There's no efficient dispersal mechanism. Once the nanoparticles are formed up there, they're going to remain there unless something drastic happens. Okay? They will eventually settle into the lower layers of the atmosphere, and they will affect our air quality. Yes, our air quality can be even worse than it is at the moment because of nanoparticles and all the health hazards associated with nanoparticles. So the health concerns are that on reaching the Earth's surface, these nanoparticles can pose health risks similar to other airborne nanoparticles, which are generated not from satellites disintegrating in the atmosphere, but from pollution and from various industrial processes. Inhalation of certain nanoparticles can be harmful to human health. You get all sorts of respiratory and cardiovascular problems. It's easy to imagine breathing in carbon nanoparticles. And the space debris contribution, the re-entry of satellites, contributes to the overall debris problem in space. There's a lot of debris, and it's increasing at an alarming rate. I'll be able to show you some numbers which have been generated in this excellent and easily accessible review article in Scientific Reports not that long ago. So the nanoparticles that do survive will always tend to accumulate in the atmosphere over time. So the nanoparticle density in our atmosphere is increasing all the time. Now, the first generation of Starlink satellites is already up. And from that, and many of them are now beginning to die, they don't have a very large lifetime. Like with many big companies, and there's a built-in obsolescence, not only in the washing machine and the refrigerator and the microwave that you buy, but apparently also in the satellites that are up there. So they decay very, very fast, faster than one had anticipated even 10 years ago. So it is expected that there are something like 2 tons of dead satellites re-entering the Earth's atmosphere every day. Every day, not annually, not monthly, but every day. That's a lot of space debris that is entering. And the astronomers are already up in arms about this because it affects their observations. So this is trains of Starlink satellites, which are ruining the astronomical observations thanks to Lovell Observatory in the US. Clearly, you can see that your astronomical observations, particularly in the visible, are tremendously affected by these satellites. Will the situation improve? Maybe this is just a transient phase. Maybe technology and the science and material science, particularly of how satellites are made, might improve the situation. Well, as I already indicated, the first generation of Starlink mega constellations are expected to consist of about 12,000 satellites in the coming months and years, okay? Of which just under 1,700 or just over 1,700 have already been launched. So a lot more are coming. Active and defunct satellites in low Earth orbit, and low Earth orbit means altitudes less than 1,000 kilometers, has already increased by 50% in the last 2 years. And as Bowley, the author of this article, wonderful article, says, the problem is that there are now plans to launch about 55,000 satellites. The second generation of Starlink would consist of up to 30,000 satellites. And then you have other non-Musk satellite systems. You have China's Starnet, you have Amazon's Kuiper, and you have, I think, the European Union's OneWeb set of satellites. In 20, 30 years, there might even be ISRO set of satellites up there as well. You know, we are generally 20 to 30 years behind in these things, alas. You know, so you can imagine that there's going to be an unprecedented change in the Earth's upper atmosphere. You know, I keep forgetting that I'm live, so now I've insulted not only Elon Musk, but I've insulted ISRO as well, Vandana, apart from the Navy. You know, the list is getting further, longer and longer. Okay. Now, when a satellite becomes defunct, those who are responsible for them have 3 possible options. Well, actually, it doesn't really, this. 2 of them are related to each other. One is leave them there as junk, which was what the initial tendency was up to 5 years ago, and hope that the burning out will be very efficient, and nobody was aware of this possibility of nanoparticles being generated as the burnup occurs. Let them fall down in bits, as is becoming increasingly popular. So break the satellite up while it is still in orbit, and then let the smaller bits come down. Doesn't solve the problem of nanoparticle generation. In fact, it might even make it more efficient to generate nanoparticles, and let them burn on re-entry. So all this leads to metal particles lingering in our planetary atmosphere. Condensation, coagulation into metal nanoparticles lingering in our planetary atmosphere. Okay, how do we know that this is actually occurring? Do we see metallic ions in the Earth's atmosphere? We do. I mean, this is a complicated slide, so let's not worry about it. I just want you to focus on this part over here, where NASA now has one aircraft, and it has a sampling hole right at the nose over here, and it flies through areas where it imagines satellites have decayed and there's particles have been burnt up in the Earth's atmosphere, and it samples those particles and takes them into a mass spectrometer system. So there's an inlet over here. It's very much similar to many mass spectrometer systems that we used to have in B block first floor. So inlet over here where the atmospheric samples come in, and there are 2 lasers depending on what type of ionization you want to occur, an excimer laser and an Nd:YAG laser. Ionization occurs, and the ions are then monitored in a time of flight spectrometer over here. And this is the nose cone over here with the sampling thingy. Okay. Sorry?
So there, the inside atmosphere gets mixed with the outside, and there is a chance.
The normal passenger aircraft are generally flying at much lower altitudes than this, right?
Yeah.
Much lower altitudes than this. But in principle, This is not a big setup. This type of thing is not a big setup. In principle, even in commercial aircraft, one could install this type of apparatus and monitor the atmosphere at lower heights, lower altitudes. Yes. So the difficulty there is that people will say, but that's from industrial pollution from the terrestrial source. It's nothing to do with my satellite, which is breaking up. So whereas at those 10 kilometers and higher, industrial pollution is unlikely to go that far up, we think. Okay, so the work that I'm going to describe now concerns the H3 plus ion. So 3 hydrogen atoms together in ionized form. And this is some work that was done recently, a couple of years ago. I want to just mention that Saeed, Rami, and Ali, and Mathur Iqbal, they are all grand students of mine. So they are grand students, is student ka student. Okay, so that shows you how old I am, okay, to have grand students. But I'm rather pleased that I can report on some work that grand students have done. And all 4 of them are also scientists working in exile because their own country is not accessible to them anymore. I'm told, I gave a talk in CBS on Tuesday, and a very eminent mathematician told me, Deepak, you would not be allowed to talk like this in IIT Bombay, because there, whatever you're going to say has to be vetted by the authorities. I don't know how that's going to happen, because I don't know what I'm going to say. So how will IIT registrar know what I'm going to say? I don't know. But yeah, so these are people who are Palestinians. Okay. Did that get picked up as well? No. So, good. Okay, so you know what the water molecule looks like. 2 hydrogen atoms and an oxygen atom. It can undergo either symmetric vibrations like this or asymmetric vibrations like this. There's a lower propensity for bending vibrations as well, but that's a very low frequency. So this is how water molecules behave normally. You can imagine from this picture that forming 3 hydrogen atoms in an ion, single ion, H3 plus, is unusual. It's exotic, right? So this is the title being justified. Forming H3 plus from here involves breaking a bond there, breaking a bond there, and breaking one of these 2 bonds, and then hoping that the 3 hydrogen atoms that have been liberated will somehow come together and form a molecular ion, H3 plus. Though it's an exotic reaction, it's actually well known. H3 plus ions are extremely well known. They're very stable. They were first seen in the spectroscopy experiments, mass spectroscopy experiments of J.J. Thomson in 1911. And subsequent work by him and others found that H3 plus ions, he also managed to do the spectroscopy of these ions, and he and others found that they are quite abundant in many astrophysical environments, the H3 plus ions. It's now regarded as the most important triatomic molecule in the universe. I believe in the 70s, a colleague called Oka also got a Nobel Prize for work on H3 plus in an astrophysical environment. Okay. Now, it is conjectured that these H3 plus ions can catalyze interstellar reactions and therefore give rise to organic molecules. And organic molecules is something that astrochemists get very excited about, because these are, of course, precursors to life. So if there's going to be life in an astrophysical environment, you need to have organic molecules. And H3 plus, if it acts as a precursor to forming organic molecules, yeah, it's worth doing, it's worth investigating. Some more students and grand students of mine, Shankar De and Jyoti Rajput, are grand students of mine. C.P. Safwan is a student of mine. This is work done at the Inter-University Accelerator Center, where they did experiments on the formation of H3 plus using the Ulta reaction. They took methanol ions, doubly charged methanol, And they broke it up and they found, whoa, wow, we can form H3 plus ions. So here I was talking about the importance in astrophysics of H3 plus forming methanol and so on. But these people have done work showing the ultra thing is also possible. Okay. What we will be doing is neither of this type of work. We will be using the technique called reaction nanoscopy to be able to study H3 plus and see whether nanoparticles have some influence on its formation dynamics. This is a reaction nanoscope. This exists at the American University of Sharjah, in the United Arab Emirates. And this is Ali Al Nasser and his students who built this. So you have basically at this end, you have a nanoparticle solution, which gets aerated with high pressure argon. So vapor of nanoparticles goes in this direction, and then part of it is extracted in a horizontal direction. There's a fancy lens system, so you can, to some extent, control the size distribution of the nanoparticles bundles that you're transmitting in this direction, transmitting due to differential pumping. So you have relatively high pressure here and relatively very low pressure over here. So the tendency is for these nanoparticles. I should also mention that in this dabba over here, these nanoparticles get enmeshed in water vapor. So the particles that are coming out horizontally are nanoparticles plus water. So there's water with nanoparticles embedded in them. Cross beam, there's a laser that comes for the ionization to occur, and the products are then detected in two directions. The electrons that are generated in the ionization process are detected in a downward direction using a channeltron, and ions are detected in a very large microchannel plate detector with position-sensitive anodes. So you can not only see ions being formed, but you can see the angle at which the ions are being formed. And if you do an experiment in coincidence, the electrons and the ions in coincidence with each other, you can easily devise strategies to ensure that the ions that you're seeing are from nanoparticles plus water and not from inevitable background vapor, water vapor that will be there in any apparatus that is there. So, well, this is what's saying the same thing that I just said. The reaction nanoscopy allows differentiation of ions emitted from the nanoparticle surfaces and those generated from background. It now enables you to discriminate the ionization events by recording electron emission in coincidence with ion emission. And you have to realize, of course, that's only possible because the electron emission signal is very much greater than the signal that you get from background gas. Okay. This is very similar. And the work that was done here with the reaction nanoscopy was more or less built on the ideas that were generated in work that was done in B block first floor some years ago, where this is another version of the apparatus, but the only difference is that here we didn't look at electrons, we only looked at ions. So again, we had a feed through with a gas jet going in this direction. We had a laser beam going in that direction, and ions that were formed were extracted in this direction on a large microchannel plate detector with position-sensitive anodes. And if you convince yourself, this little dot over here is the focused laser beam. So it's a very small and well-defined interaction zone. So interference from backgrounds is likely to be minimal. Okay. So even without doing the electron and ion coincidences, you can be pretty sure that the signals that you're getting are Baca signals from the reactions that you want to study. Okay, going back to the reaction nanoscope, going back to the Sharjah experiments, so this is a typical mass spectrum that one would get when one puts in either H2O or D2O without nanoparticles at different laser intensities. You get, of course, the H plus ion and the D plus ion very prominently. This is a log scale and some junk over there, which is not worth bothering about. The laser intensity doesn't seem to have too much of an effect on the variation. Okay. This is again the same thing. The red curves are more or less the same as here, but the blue are when you also now turn on the nanoparticle in that source that I showed you. So now you have water, H2O or D2O, with the nanoparticles, in this case, silicon dioxide nanoparticles embedded in them. And now you can see that in addition to the H plus and the D plus, and the D plus could also be H2 plus, with the same mass to charge ratio, you also get other species coming out. You get H3 plus, D3 plus, HD2, and H2D plus. So these additional ions, and remember this is a log scale. So this blue stuff that has suddenly come because of the presence of silicon dioxide nanoparticles is remarkable. It's a lot of enhancement of signals which were not there before without nanoparticles. You could do this experiment with a couple of different, we did only 2 different sizes of nanoparticles, 100 nanometer and 300 nanometer diameter silicon dioxides. And as I told you, this is done by messing around with apertures, nicely designed apertures along the injection system. So it's more, take it with a pinch of salt that is 100 nanometer, and it's equal pinch of salt that is 300 nanometers, is there or thereabouts. And you can see you get H plus, H2 plus, and H3 plus. For the molecular ion, there's no difference really between the size of the nanoparticles, but for H3 plus, there's about a factor of 2 difference with the nanoparticles. You get much more H3 plus with 300 nanometer silicon dioxide than with 100 nanometer silicon dioxide. So that may be a clue as to what's happening. I don't know. Okay. Of course, one tries to do experiments with pure H2O, not that difficult, and pure D2O, extremely difficult, because the D2O that you buy will always have contamination from H2O, no matter how much money, and it's a function of how much money you're willing to spend to get purified D2O. But you'll never get 100% D2O. There will always be some H2O in it. Typically, it's about 60% D2O and about 40% H2O. Okay. Now, I said that we have a big microchannel plate detector with position-sensitive anodes, so you can actually map the momenta. So looks like it, yes, looks like it. Yes, from 100 to 300 nanometer. No. This is brute force ionization. Right, so the color of the laser beam or anything like that doesn't matter. You're just kicking the hell out of these ions and overcoming the Coulomb potential. So this is what the momentum distribution looks like. We can convert those time-of-flight mass spectra into momentum spectra, and this is the propagation direction of the laser. And you can see that along the laser propagation direction, there's a propensity for more H3 plus. Right angles to the laser propagation, there's less, and opposite the laser propagation direction, there's much less H3 plus that is being found. So that's another clue that one might be able to work on to try and find out what's happening. From these momentum distributions, it's not difficult, classical mechanics, to be able to work out what the energy distribution of the H3 plus ions is. And this is what the energy distribution looks like. It's a very broad distribution from about 5 EVs to 30 EVs. It's a lot of energy, by the way, per H3 plus ion. Okay. And the peak is about 15 EV. I'll show you more of these type of energy distributions and then make a point about this. So yeah, you mean the red parts, right? Yeah. We need to do this many more times to be sure of what that structure means. I mean, we barely understand what's happening right now, and now you're telling us to understand even more. But that may be, yeah, but we have not been able to reproduce those red structures unambiguously. Something is happening, but we don't know. And the conjecture is that why you're getting maximum intensity of H3 plus along the propagation direction is to do with near field enhancement, near field effect, surface plasmon resonance type of work that used to go on in our lab when we were working on larger rare gas clusters. So you, yes, the red part is, that's exactly what Carla was also asking, you see. The red part is not symmetric for reasons that we are not sure how reliable that. We have to do this experiment many more times to be able to get reproducible red parts. No, the statistics are pakka. They're good. I can't remember. I can't tell you. If you look at the paper, the supplementary materials will give you exact raw data. Sorry? Yeah, but it doesn't tell you counts over what period of time. Okay. Yeah. Yeah. These are coincidence experiments. They're extremely difficult to do. So the count rates will be very, very low. In fact, you deliberately keep the count rate low so that the effects from background are negligible. Okay. So that will be 40 counts, I would estimate, over 8 hours. Also.
Kilohertz laser.
It's a kilohertz laser.
Had it been megahertz, would have been further better.
Yeah.
Time would be more.
Yeah. I don't know. You know better. Megahertz of these intensities? 10 to the 14, what specifically? 10 to the 14. Okay, fine. All right. It's delay gate anodes. Okay, it's not phosphor screen. In the TIFR version that I will show you, it is phosphor screen, very large phosphor screen. Here it's delay gates. Yeah. Now again, momentum distribution. That was the previous work was with 300 nanometer silicon dioxide particles. Now we do the same thing again with 100 nanometer silicon dioxide particles. And you can see, I mentioned to you that it's a factor of 2 less intensity for H3 plus, and that reflects in this. Now you can see, Carlo, there are red dots all over the place. Okay, but nevertheless, you can still derive an energy distribution from all this. And the energy distribution is more or less the same from about 5 eV to 30 eV with a peak at about 15 eV. Okay. And that's again, 15 eV is the number that I'd like you to keep in mind for a little bit longer. The signal for D3 plus is even weaker than the signal for H3 plus. Even now you can see a sprinkling of red dots. I hadn't thought about red dots before, but there we are. So this is D3 plus on 100 nanometer silicon dioxide particles, and more or less the same type of distribution. Oops. About 5 eV to about 30 eV, with again, maximum, most probable energy being about 15 eV. So the number 15 remains constant. It's a very energetic H3 plus and D3 plus being formed. Now, this is work done at Tata Institute on D block first floor again. So this is, okay, this is looking at mixtures of H2O and D2O and how do we distinguish what the percentages of H2O and D2O are. We do vibrational spectroscopy. I'm not going to talk about this talk over here, but I am going to mention momentum maps that we measured for the H plus ion coming from H2O and the D plus ion coming from D2O using a phosphor screen, in this case, a fast phosphor screen. Okay, so, oh, sorry. Yeah, I pointed to the wrong phosphor screen. You're both wearing blue t-shirts, so it's difficult. Yeah. Okay, so now if we look at the energy distribution, so I'm not going to plot the curve of the energy distribution. You see that the peak energies are not anywhere near 15 eV, but they are 3.4 eV with another clump of about half an eV in this direction. Okay, and again, the peaks are, this is the laser propagation direction here. And now those red dots are pakka, that's peak intensity. This is what the curve looks like. The energy distribution shows you that for H plus and for D plus, you get 2 peaks, sort of a 1 eV type of peak and about 3.5, 4 eV type of peak in both cases. All this is done with 10 femtosecond pulses. So whatever is happening to the 2 H2O molecules, or more than 2 H2O molecules, the rearrangements that are taking place and bonds being broken and bonds being reformed, new bonds being reformed to give you H3 plus is happening very, very fast. It's happening on time scales of less than 10 femtoseconds. Okay. I don't know. That's a surprise to many chemists, but for laser people, it's no longer a surprise. It used to be a surprise, but it's no longer a surprise. And we've tried to rationalize that with quantum chemistry calculations. I'm not going to talk about that. The point is that when you do the same type of experiments with not just H plus, but HD plus as well, you find that similar things happen. The energy distributions are very different, of course. Instead of 3.5 eV or so, most of the energies are much lower. They're about 1.5 eV to 2 eV. But again, the point is that H atom migration that occurs to form H and D plus is on very, very fast timescales, less than 10 femtoseconds. Okay, this is more of the same. Okay, so comparing the H3 plus in the reaction nanoscope results, we can, I think, unambiguously claim that nanoparticles not only act as catalysts to form these ions, H3 plus and D3 plus, but they also lead to an enhancement of their energy and momentum. And this is because of near field effects, something akin to plasmon resonances, okay? Localized field intensity enhancements. Now, you might well say that, okay, that's a very specialized, narrowly defined experimental situation where this might be happening. But one has to realize that conditions in our terrestrial laboratory might indeed be replicated in nature as well. So instead of silicon dioxide nanoparticles of 100 nanometer size and 300 nanometer size, you have complementary situations in the astrophysical environment. You have dust in the inner heliosphere, and you have planetary debris disks around other stars that do include nanometer-sized dust particles. So the size of these nanoparticles in our laboratory is nothing unique as far as nature is concerned. There are other astrophysical environments where these nanoparticles exist in similar types of sizes. Might these dust particles act as catalysts for the formation of H3 plus up there? Well, what about the others? There are no intense lasers over there to do this type of work, right, to do the ionization. However, you do have these nanoparticles being collided by cosmic rays of charged particles and by the solar wind of highly charged ions. And work done again in this institute has shown that there's an equivalence of the fields that are generated by intense lasers and fields that are generated in heavy ion collisions. And the physics that turns out because of these high fields in the two cases is very similar to each other. So though there are no intense lasers up there, there are equivalent generators of high fields up there. There is some attempt we've made to, I don't like this slide at all because it's really hand-waving. One of the penalties of publishing in a journal like Nature is that they insist on vigorous hand-waving. Whether the hand-waving for creating a model is valid or not valid or of limited validity, they don't care. So they insist that we do some sort of hand-waving. So we've done some hand-waving of these models. So we have two different types of hand-waving. So we have this nanoparticle surface. Nanoparticle is being bombarded by, being irradiated by the intense laser beam over here. And you can imagine, this picture is a bit slow, but you can imagine the H2O molecules over here. In this case, in the left-hand panel over here, one of the hydrogen atoms is embedded into the, stuck onto the silicon dioxide surface, as is one of the hydrogen atoms in this other hydrogen molecule. So you have pairs of hydrogen molecules which are connected to other hydrogen molecules. And as the migration occurs, it leads to formation of H2 plus formation. These H2 plus molecules, ions, roam along the surface close to each other and ultimately lead to formation of H3 plus. Well, I don't know, this is with a water dimer and this is with roaming mechanism involving water molecules, single water molecules. There's one paragraph we wrote about this because we didn't dare write anything else. So this is not a very satisfactory explanation. It's certainly not an explanation, but it's hand-waving. Nanoparticle is facilitating the embedding of these, either a pair of water molecules or water dimers, creation of water dimers, which then roam. And as they're roaming and as the vibrations are occurring, you have situations where two bonds can be broken and reassembled in a different way. That's the conjecture. Right? Ideally, one should have a tame quantum chemist who should be able to do this type of calculation using quantum mechanics. But we don't have either a tame or a wild quantum chemist. So Anybody here is a quantum chemist? So nanoparticles, the bottom line seems to be, nanoparticles do catalyze exotic molecular reactions, molecular processes in the Earth's atmosphere, and they probably do so in other astrophysical environments. Whether these exotic molecular processes in themselves are beneficial to our health or not beneficial or harmful to our health remains to be seen. Probably that's a neutral. The answer is in the neutral. We don't know. But what is certain is that the propensity for increase in nanoparticle density in the Earth's atmosphere because of satellite breakup is harmful. And it's hardly talked about, not realized at all by people. So I rely on you guys to make sure that next time the news tells you about satellite launches being successful and things like that, what goes up is as a satellite actually comes down as debris and contributing to formation of nanoparticles in the Earth's atmosphere. So thank you.
For questions?
Yes, Georgie.
PM2.5 concentration or whatever pollution. See, in comparison, if you compare the concentration of PM2.5 or PM10, the most harmful ones in atmosphere, what will be the percent of this debris-related polluted? It could be minuscule, very small. So should we worry about it?
Depends on the altitude you're talking about. And the type of altitude where the measurements have been done, which is 10 kilometers and above, the other terrestrial pollutants are in very small abundance. Okay. Up there, there's only these guys. Ultimately, these guys will also trickle
Better.
downwards. But at the moment, there is no such information that I'm aware of.
Lab experiments that you have done, this done only with silica or some other?
Yes, only with silicon dioxide, yes.
I mean, there is any reason for choosing silica? Because, I mean,
No, that's what was available in the lab.
I see.
Yeah, usual
Okay.
thing. Sorry, but that's how.
No, but
that's how
any
science
other,
progresses.
like aluminum, I mean, other
We could
metals
try
or
aluminum
something?
particles as well, yes, but we haven't. Not in this series of experiments.
Okay.
Yes,
Right.
Sushil.
You probably covered this earlier, but up to what altitudes do you expect these nanoparticle generated species to?
Well, the measurements, the Pakka measurements, aircraft measurements have been done down to 10 kilometers.
Oh, that's tropospheric.
So there may be more at lower altitudes, we don't know. There's only one aircraft from one agency doing this type of work. I mean, unless the Chinese are doing it, they're not going to be telling you, you know. So.
Our balloons can measure. Our stratospheric balloons can
Well,
measure.
your balloons, the TIFA balloons can go up to 40 kilometers.
We can.
Yes. 50. Wow. Okay. So there you are. You can persuade whoever is Manchanda's successors in the balloon facility to consider this.
Yes, question and a comment. Comment is simpler. I thought you can get much purer D2O. The reactor people don't use 60%.
Very, very expensive. Very, very expensive. Yes.
It's
Yeah.
important time.
For colleagues in Sharjah, expenses not generally a consideration.
Okay.
That's true. Yeah.
What's the structure of H3?
It's a triangle.
Huh?
It's a triangle.
Triangle.
Yeah. That's been established many years ago
Yeah.
by what they call Coulomb explosion imaging.
But then you will get a lot of information from Raman.
From?
Raman.
There probably are Raman spectra of H3+. Yes, indeed. Sure.
No, even formation and all that, because
The formation of H3+ is sort of understood by us and others from work done here. But in the context of increasing the propensity by means of nanoparticles and increasing the energy content from about 3 eV to 15 eV. That has to be understood. 15 eV per H3 plus is very, very impressive. That's a lot of energy up there, you know.
Last slide, when you show H3 of migration, can you not imagine in times of
Yeah. Yes, the answer is yes, we could, but we haven't. Yeah, you're right. Yes. So far, we haven't done that. Yeah. It's an obvious extension, isn't it? Yeah.
Anybody from Zoom has
come
a
and- come
question?
and-
They can
come and
unmute
do it.
themselves.
Come to Sharjah and spend a month or two to do it.
I think we can all join in appreciating the lecture which we have been delivered and things. Thank you again, Professor. Before we all go, I have another one business which we want to convey. Yeah, as you are all aware, Professor has already mentioned his long association with Asset Forum as such, and he has delivered, hopefully, as he was mentioning, by 5 p.m. he will be amongst the toppers. And then
Well, not 5 p.m. anymore because I finished my talk. So I am now.
Yes.
Oh, yeah. Right. Give me my certificate.
So I request Satyaji to, as you are all aware, about a few months back, we had celebrated 40 years of Asset, and we did remember you at that time. And Satya told me to please remember whenever you come down and give an Asset curriculum to hand over this memento for you to appreciate.
Yeah, before I enjoy this pleasure of giving this memento to him, I think I already shared earlier, but I want to repeat because it's there. So it was Professor Deepak Mathur who asked me to lead coordinate Asset in January 2002. So in some way, you have been responsible for everything what I have done in the Asset. So thank you very much on my personal behalf, but also more importantly, from the Asset, it will be great pleasure to give you this.
Thank you.
If you are present on that day, of course, you would have been the first one to hand over, but it turned out that you were not there. So it's a great pleasure for all of us.
Thank you.
To hand over this. Thank you. Thank you, sir.
So the Vice President.
Thank you, Carlos.
I'm very happy to see you.